we're ready for the last talk of the Categories and Companions Symposium. So Joshua Wrigley will be telling us about from Lindenbaum algebras to classifying toposes, number 2, the geometric completion of a doctrine. So if you're ready, take it away, Joshua.
Cool. Thank you very much. Thank you to the organizers. Yes, as you can sort of guess by the 2 in the title, this is a sequel talk I enjoyed the Categories and Companions Symposium very much last year. And I think the organizers have done a great job uniting people across time zones. So yes. So this talk begins with the previously on section, and I won't make specific references to what I talked about last year. But in my presentation last year, I tried to sort of give credence to this slogan that we should be thinking of locales and preorders as models of propositional logic, as Grothendieck topoi and categories are to first order logic. And I gave a very loose analogy between some sort of things we see in propositional logic, such as preorders, the free join completion, the locale of ideals giving once we're given a covering system. And I compared those to constructions we find in toposphere and their relations to first order logic. And, you know, I admit that it was a sort of fairly loose analogy. So the onus of this talk is to rectify that analogy and make it stricter. And we're going to be using the language of doctrine theory to do that. So I'm going to be arguing this time that preorders are going to, their natural first order logic generalization should be doctrines. The free join completion should give rise to a free geometric completion. Covering systems and Grothendieck topologies is still a fairly good analogy, and we'll be looking at how we go from a locale of J-ideal style construction to a geometric completion, as well as the topos of sheaves on a site. So to give a very brief rundown of what I talked about last time, we'll give the propositional side of the story. So let's say you're given a meet semilattice, which represents some propositional theory with conjunction being interpreted. And you've got a covering system, which will be some extra rules on top of your preorder. And there exists a frame, the J ideals on P, such that for any finite meat preserving map, F from P to Q, where Q is also a frame, we have a unique extension that is a frame homomorphism. And so, you know, we can start making logical sense of this, and this locale of J ideals is being some sort of completion to geometric propositional logic. And if you are fine transferring between internal and external languages of a topos, then the talk ends here for you, because what I'm going to be presenting is the internalized construction of a locale of J ideals for some internal preorder and some internal covering system. So I'm going to be talking about the language of doctrine theory, so I should introduce doctrines. Now, a doctrine is just going to be a functor from a category C into preorders. Now, the category C is going to represent, in this logical understanding we have, the types of our signature, and the arrows are going to be morphisms between those types, maybe relabelings of variables. And each fiber of this functor is going to be the preorder of propositions for that type. And so, you know, we have, at the moment, this definition doesn't carry a lot of syntactic information, but we can make stricter and stricter examples. So we could have primary doctrines where our base category has finite limits and our functor P takes values and meets semilattices and their homomorphisms. That's going to be a doctrine which interprets logical conjunction. We can have existential doctrines where we add existential quantification. So we're going to have the left adjoint satisfying Frobenius and Beck-Chevalley. We can have coherent doctrines where we include logical disjunctions. So we now take values in distributive lattices, and we can even go all the way up to Boolean or classical doctrines where we're taking values in Boolean algebras, and each map not only does it have a left adjoint, but it also has a right adjoint interpreting universal quantification. So how do we make sense of all of this extra information? What are the models that we're going to associate to a doctrine? Well, a model of a primary doctrine is going to be consisting of a pair. It's going to consist of a left exact functor from our category of types into sets and a natural transformation from P to this functor on the bottom, A op P. Curly P is the power set functor. So we're going to, the functor A is assigning to each of our types a set, and we're now picking a meet semilattice homomorphism from our fiber of propositions to the power set of the set. And so because we've got meet semilattice homomorphisms and A has to be left exact, this is going to preserve all of the conjunctions present in the theory of the doctrine P. But if we wanted to talk about richer syntaxes like we saw on the last slide, we start to have to make restrictions on what type of models we consider. So, for example, if we wanted to do coherent doctrines, we'd require each of the components in our natural transformation to be a distributive lattice homomorphism, and we're going to also require the squares of the existential quantification to also commute. So we just have to require on top and make restrictions that all of the added structure that we care about is also preserved. But what if we wanted to treat a lot of different theories with different syntaxes in a more uniform way and come up with some sort of syntax invariant way of dealing with doctrines and touching doctrines? And for that, that's where Grothendieck topologies come back into the story. So on this slide, I just give some notational conveniences. So we're given a doctrine, we have the Grothendieck construction for this functor. So its objects are going to be pairs of something of the base category, something in the fiber over it. Arrows are going to be arrows of the base category, such that the image of, we've got an arrow from X to the image of Y under the transition map. And of course, once we do that, we're going to get a fibration. And because P takes values in pre-orders, this is actually a faithful fibration. And we're now going to consider Grothendieck topologies on this category. So I'm not going to give a in-depth description of what a Grothendieck topology is. It's a bit technical, but suffice to say, a Grothendieck topology encodes some notion of covering on our category. It's going to say when some family of arrows covers something in the domain. And by varying that Grothendieck topology, it allows us access to the models of the pre-order P according to various different syntaxes which might exist on P. To do that, we're going to use the notion of a J-flat functor. This will be very familiar to anyone who's seen some topos theory before. We're going to call a functor, a left exact functor, so preserving all finite limits, M from C times P into sets. It's going to be called J-flat if the J covers, some Grothendieck topology J, are all sent to jointly epimorphic families in the category sets. And then we have our examples, and we see that all of the examples of doctrines that we gave at the beginning have their semantics in terms of a Grothendieck topology. So for primary doctrines, that's just the same as taking the trivial topology, where only identities are covering. when we want to model an existential doctrine, when we want our existential quantification to be preserved in our models, then we vary it and take the existential topology. That's the topology generated by covers of this form here. And coherent and Boolean doctrines are both covered by flat functors for the coherent topology. And the coherent topology is defined by having covers, is defined to be the topology generated by covering families of this form at the bottom. And so we can see that by modifying which Grothendieck topology we take, we modify which syntax we are preserving when we take our category of models. And so, just to belabor and stress the point again, Grothendieck topologies allow us to uniformly talk about a large class of syntaxes, possible syntaxes on pre-orders, not all, but a large class. So now that we've covered all of the introductory material, let's see the main question that we're looking to answer. And that is, given a doctrine, can we universally complete that doctrine to a richer structure? Phrased in another way, if we're continuing the logical analysis, if we're given a first-order theory, are we able to find a theory in a different syntax which is semantically equivalent? And, completions of doctrines have been considered a lot in the literature. So I'll just give some examples. We've already seen one at the beginning, the free join completion. So whenever we have a pre-order, this free join completion, which also appeared in Dirk's talk earlier, satisfies this universal property that there's a unique extension of any map into a join complete pre-order that preserves all joins. The second example is from David A. Trotter's paper, The Existential Completion. So if we're given a primary doctrine, we can find a way of universally adding existential quantification to that primary doctrine, so that we get this doctrine P superscript exists, that has this universal property that, for any morphism of doctrines, where Q is an existential doctrine, then we've got a unique extension that preserves the new existential quantifiers. And so we turn to the title of the talk. We're going to be completing to the data of a geometric doctrine. So a geometric doctrine, here we're only considering it over a category of all finite limits, is going to be a doctrine that satisfies one of these equivalent conditions. The first two are fairly obvious to see that they're equivalent. It's going to be a geometric doctrine is going to be a doctrine that is coherent, but also takes values in frames and frame homomorphisms, or equivalently, it's going to be a functor into frames and open frame homomorphisms that also satisfies the Beck-Cheveley condition. And finally, this is equivalent due to a result by Joyaux and Tierney that P is an internal locale or internal frame of the pre-sheaf topos sets to the COP. So this is the data of a geometric doctrine, and we're going to build a completion to this data. So, you could prove all of the results I'll mention at the end by hand, but it's just so much easier and nicer to use some fancy topos theory. So let's do a quick recap of some results from topos theory. We're going to say that a geometric morphism, which is the type of morphism we consider in topos theory, a geometric morphism between two toposes F and E is going to be said to be localic if for any object in our domain topos, there's going to be a diagram of this form where we've got U, F being covered by U, where U is a sub-object of something in the inverse image. And some classic examples of localic geometric morphisms include subtoposes. Embeddings of subtoposes are always localic. Any geometric morphism induced by a faithful functor is also going to be localic, and any geometric morphism between two localic topoi are also going to be localic. And now some basic facts about localic geometric morphisms are that, firstly, there exists a unique isomorphism internal locale L such that F is the sheaves on that internal locale. So here, when we take the topos of sheaves, we take as a site the Grothendieck construction for our internal locale L, and we apply this Grothendieck topology onto that category. And KL is going to be the topology generated by covers of this form. And that is very reminiscent of the coherent topology, except this time we're allowing infinite disjunctions. And so that's where the geometric flavor is beginning to be introduced. So yes, if we've ever got a localic geometric morphism, we can take that the domain topos to be the sheaves on an internal locale. And the second result is that whenever we have two localic toposes, we've got two geometric morphisms which are localic over the same codomain topos, then any geometric morphism between those two toposes, making this triangle commute, is going to be induced by an internal locale morphism. And so an internal locale morphism is going to consist of frame homomorphisms between each fiber, such that those frame homomorphisms are natural with respect not only to the transition maps, but also the left adjoints of the transition maps. You could think of it as we have a morphism of doctrines which preserves all of the geometric structure of those doctrines. Okay, and now we can define the geometric completion very easily. We're given a preorder, we're given a doctrine, and we're given a Grothendieck topology on its Grothendieck construction. Now, the composite geometric morphism here is given by a localic geometric morphism, an embedding of a subtopos, followed by another localic geometric morphism. It's induced by that faithful vibration we saw earlier. And so the composite is localic. And so sheaves on C times Pj is the sheaves on an internal locale. And we define the geometric completion on the pair Pj to be the corresponding internal locale. Now, we can immediately use those facts that we saw earlier to give proofs that it's the universal such completion. So if we have our doctrine P and we are given a geometric doctrine L over the same base category, if we have our topology on C times P, then for each morphisms of doctrines A, which preserves the J covers in this sense, that if we've ever got a covering sieve S on this pair CX, then the morphism of doctrines A preserves those J covers in the sense that we have this equality. This is equivalent to saying that the image of a sieve is KL covering. Then we can use the universal property we saw earlier that there exists a unique internal locale morphism of math such that our morphism of doctrines A factors uniquely as the embedding of P into its geometric completion, followed by this internal locale morphism. So we're preserving all of the new geometric structure at the end. So, you know, that's very easily seen because such a map A is going to induce a geometric morphism here at the top of the horizontal component of a triangle, and it's commuting with the two projections into the pre-sheaf topos. And so we have a geometric morphism between two sheaves on internal locales. It's going to be inducing a morphism of internal locales. And we also get that property I was referring to earlier, that the semantic invariance, that if the Grothendieck topology J is describing the models that we want of our doctrine, then the geometric completion is a semantically invariant or Morita equivalent doctrine. Its models are the same, and that's immediate by Diaconescu's equivalence. So what have we done? We've created a completion for a doctrine which is semantically invariant. We have taken a theory that perhaps we don't like the syntax involved in that theory. We found a geometric theory which we do like, and we've shown that working with a geometric theory suffices to describe all of the semantics of the theory we started with. So let's have a look at some example constructions.
Sorry, just to let you know, it's been about 20 minutes. How much longer do you have left in the talk?
I can hopefully wrap up in about 5. Is that okay?
Yeah. I mean, maybe is 3 possible so people have some time for questions before the end of the...
I'll try and be as fast as possible. Sure.
Cool. All right, thanks.
So we've got a primary doctrine. The trivial topology is always a Grothendieck topology on any category. And so that is going to be the free geometric completion, where the only structure we're preserving is the logical conjunction. We can do a geometric completion for the existential topology on an existential doctrine. When we do that, we observe that it acts on the fibers just by the pointwise free join completion. And, there's this kind of cool result, which I find interesting, that if we've ever got a primary doctrine P, we can perform the existential completion and then perform the geometric completion on top of that. And that's the same as taking the geometric completion, the free geometric completion to begin with. So, and you get similar results if you freely add any geometric structure to your doctrine P. As long as you keep track of that with the Grothendieck topology, then it's the same as if you just geometric completed in the first place. We also see that it's got fairly natural connections with the completions we see in propositional doctrine theory. So for coherent and Boolean doctrines, it's the same as taking the ideal completion to coherent frames or stone frames. And if we've ever got a geometric doctrine and we take its geometric completion with respect to that topology KL, we actually get something back which is equivalent. And so in particular, the geometric completion is idempotent. So we've got a completion which has a universal property and it's idempotent. We're expecting to get some sort of idempotent monad out of this, and indeed we do. I just need to quickly describe what the category that monad is working on. It's the category whose objects are pairs consisting of a primary doctrine and a Grothendieck topology on its Grothendieck construction. And arrows are going to be morphisms of primary doctrines such that J covers are being sent to K covers. And, I've called this category primary doctrinal sites over C. That's not a good name, but it suffices to just write down this last result, which is that the geometric completion is an idempotent monad on this category whose algebras are precisely the geometric doctrines. And hopefully that's been less than 3 minutes. Thank you very much.
Awesome. Let's thank the speaker for an awesome talk. And can we end the recording?